And finally, question 8 is kind of a light check of some of our work with building mathematical models that describe situations. This was a very small set of data. You can see I have several x values that are given, and I have corresponding y values. And also, I produced and gave you the least square regression line. So that was not something that you had to do using either Desmos or your TI calculator this year. Again, the least square regression line is the equation for this line, and this is a line that attempts to model what's happening within the data, right? It's checking out the behavior of the data. And you can see that it does a fairly good job of describing generally what's happening, but it's not perfect, right? And um, I think probably like the best looking point I have is this one. You can see that that one's super close to what the model says it should be, but other ones have errors, and even that one has errors. And these errors have a name, right? The error is the difference between this what the model predicts and what the data point actually is. And you can see all of them have them, and each of these errors are called residuals, right? It's the residual. And a residual is just the difference between what the model says, right? Actually, it's the difference between a residual is the difference between um, the actual y value, that's the y value that we read from our data table, and the y value that's predicted by a model. And I do ask you to find two residuals. I ask you to find the residual for A and the residual for B. If I was to look at and find the residual for A first, that's going to be the difference between, again, the actual and the predicted. The actual value of A, right, is the y value at this point. It's 1.8. That's the value that I read for this data point A when A is 1. I'm sorry, when x is 1, this is point A. When x is 1, the model says it should be 1.8. Or not the model, the data point stored in my table is actually 1.8. There's another value here, right? It's the value that the model says y should be, right? This is the y value that's predicted, or the predicted y value. And we calculate that predicted y value by taking the x value from our data table, right, which is 1, and simply plugging it into the least square regression line. So if x is 1 goes into there, I can see that this is going to become, okay, if x is 1, this is going to be 1.07 plus 1.90. So it's going to be 2.97. So my predicted y value is 2.97. So I can see both of the things I need. I can see that my actual y, the one from the table, is 1.8, and my predicted y is 2.97. So if I grab my calculator, we can quickly calculate that value. So I'm going to take my actual y value, which is 1.8, 1.8, and from that I'm going to subtract my calculated or predicted y value, which was 2.97. So my model says I should be getting 2.97, but the actual value stored in my table was 1.8. So I can see that the model is off, right? And my residual is negative 1.17. So that's a nice observation, right? First of all, if I've got data points that are below the model, they're going to have negative residuals. So I think I'm ready to answer a couple questions. First one is, how many of the data points have negative residuals? Well, I can see that those are the ones that are below the model, and I can see that there's exactly 1, 2, 3 of them that are below the model. So we'll say that three of the data points have negative residuals. B says, how many of the data points have positive residuals? Well, I can see the ones that are up above the point. I'll use this purple. I've got, oh, that's still the black pen. I've got one, oops, I'm sorry. 1, 2, 3, 4 of my data points that are above the model. So I will say four positive residuals. C, find the residual for point A. And point A has an x value that's 1, and it's got a y value. The actual y value in the data table is 1.8. And when we did that, we found that the difference, it was negative 1.17. So that data point had a value, it was below the model, and it has a negative residual. The other one here is find the residual for the point where x is 3 and the actual y value is 6. So let's grab the calculator and go ahead and calculate the we need to calculate the predicted value. So for this, I'm just going to take the 1.07. I'm going to multiply that by 3, and then I'm going to add to that plus 1.9 equals. So I get that the model is predicting 5.11. So if I come in here for point B, I see I'll dot here. The predicted value is, this is the y that's predicted by the model. The y that's predicted by the model is 5.11, and the actual y, the one that I read in my data table, was exactly 6. So I need to find the difference between the actual y and the predicted y. So grab the calculator, and I'm just going to get back up here. Number 6, not 5, not 5. I'm going to take 6, and that's the actual minus the predicted of 5.11, and I get an answer of positive 0.89. So the residual for that point is positive 89. And those are the first four answers there. So again, this is, a very narrow question. It's not asking a lot. There's a lot of different things we can ask in this domain. So kind of be thinking big picture, what's happening here. And also remember, don't neglect those skills, because we'll need them still. How do you find a model in Desmos if you've got a collection of points, right? Don't forget how we do that. It's pretty quick, pretty easy to do in Desmos, and we can do that with our exponential functions that we're discovering and thinking about now. And then the final question says that Richard thinks that the correlation coefficient R for the data is 2.5. Explain why you know that Richard is incorrect. So let's stop right there first. Look, Richard's incorrect because correlation coefficients range between +1 and -1. And just as a reminder here, if you have a data set, right, you've got some slope, and all of your data points are perfectly on a line. Like this is like if you took a function, created a data table, and then you plotted those points, right? You're going to get all the points living exactly on the line. Your correlation coefficient R here is going to equal exactly 1. So that's one possibility. The other possibility is still perfect correlation. The only difference is that instead of having this positive slope, you would have some relationship where the slope was decreasing, and yet all the data points are perfectly on the line, right? So that would be the instance where we would have a correlation coefficient of -1. And the only values that are possible for R are things that are in between those two. So R can be anything that's greater than or equal to -1, but less than or equal to 1. So for Richard to claim that he has a correlation coefficient of 2.5 is completely impossible, right? That's never going to happen. It doesn't even make sense. And then as far as, so that's one, that's the first part, right? Richard's wrong because correlation coefficients live between the numbers -1 and +1. That's the only things that are possible for correlation coefficients. And then it says give an estimate for what you think the correlation coefficient is. Well, first of all, I know that it's positive because it's increasing. And as I look at it, the data points, they're certainly not exactly on the line, so I wouldn't say it's +1. But remember, as data points, like this might be like a correlation coefficient of, I don't know, maybe something like 0.9 or 0.87, right? Rough estimate. As these data points, as I've got more and more data and it's further and further away from the line of fit, yeah, I probably still have a almost the same relationship, but because more of my points are further away from the line, the correlation coefficient is going to decrease in this setting, right? It's going to move away from +1 to +9 to zero point 0.7. Still going to be positive, but it's getting closer to 0 and further away from 1 as the data points scatter more. So it's kind of a way of me measuring how much scatter there is from the data. All right, so that's it. That's it for the last question on the test.